now choose your type of the feature you want to have.
I'm sure morning lectures have gotten your creative juices working, so start thinking about it.
Okay, so I think we should now get started. So the first lecture of this afternoon is Cristina Marchetti from Syracuse University to discuss active and driven social methods.
Thank you. And so thanks for inviting me here. It's always a pleasure to come back to Boulder. There'll be a bit of a change of pace. I'm going to try to tell you about a type of system that we've been calling active systems. This microphone has a lot of feedback. No? It's okay? All right. That consists essentially of many interacting individual components or degrees of freedom that are driven internally out of equilibrium, and as a result exhibit a rather rich collective behavior on large scales. An example you might like to keep in the back of your mind is a dense suspension of bacteria in a dish. And I'll be giving 4 lectures, and today will be a little bit of an overview. I'll tell you a little bit, I'll give you some description of the kind of system I'm talking about, and in the next lectures we'll get into more details. But the goal of the lectures is going to be to try to see how far we can go using the tools on equilibrium statistical physics and condensed matter physics to try to model theoretically some of the behavior of these systems. I wanted to list here a few names of the people who have helped me understand a little bit about the system, and in particular, the ones in blue are former or current students and postdocs and are alumni of Boulder schools, or actually current participants. So quite a few people have been through here, and they've all benefited of it quite a bit. Is it too close, is that it?
No, I think you have to close to the...
What's that? I'm too close to the thing. Okay, I will move. Hoping I can move down to the page or the it's okay, we should be okay. But then I'm in front, because I should move at the other end. That might be too much. Alright, whatever. We'll figure it out. So as I said, today I'd like to sort of introduce the kind of systems, and then we move on the tools we use to describe them. So this lecture will be a little bit descriptive, a lot of pictures, and only towards the end I'll tell you a little bit about the basic idea and tools I want to develop, which is essentially the use of hydrodynamics as an effective field theory. And then I will spend the next lecture illustrating how hydrodynamic description of this kind of system can actually be developed phenomenologically, and what are the kind of outcomes of such theories. And then I'll spend the other 2 lectures about showing you actually how a hydrodynamic description can actually be derived from a specific microscopic model of this kind of systems, and we'll actually work through some details and derive the equation. So you'll find in the slides an overview of the contents of the lecture. We will not spend a lot of time on it right now. So what I'll do today is, first of all, I'll give you some examples of the kind of systems I want to think about and their behavior. And then I'll review, I think, some really rather simple idea on how you go about constructing a hydrodynamic theory for this kind of many-body systems, phenomenologically, reminding you of the notions of conservation laws and broken symmetries, which play a crucial role in this kind of problems. And I'll do this using a very, very simple example, hydrodynamic of a simple isotopic fluid, which probably all of you have heard about, but it would be useful also to establish some sort of a common language. So let me give you first of all some examples of the kind of systems that I would like to try to describe in some kind of unified way. I mentioned already bacterial suspensions. Another example could be school of fish, although there is a difference actually. These are inertial systems. I'll be talking about over damped systems. This will become more clear what I mean shortly. So suspension of bacteria. Mixtures of cytoskeletal filaments and local proteins, which are components of the cell cytoskeleton. The cell cytoskeleton itself, or also systems that are not living, such as layers of vibrated granular rods, of people have been building nanoparticles in solution which are propelled by catalytic self-generated forces and behave collectively as a as a collection of bacteria, if you like, or even collections of robots people have been studying those as well. So what is common to these systems? So generally, as I said, there are collections of interacting units which are cell-driven, that is, the drive that maintains the system out of equilibrium is on each individual, not at the boundary, as is more common for many non-equilibrium systems. And they exhibit emergent behavior at large scale. These are actually images of flocks of starlings that people are studying. There is a group in Europe, especially in Rome, are studying both experimentally and theoretically the behavior of these flocks as if they were actually macroscopic, deformable, soft bodies. And it's actually very interesting how you can use condensed matter physics to understand the behavior of these systems. So this system exhibits quite a robust collective behavior, even in the presence of noise, which is usually there, but although it's generally not thermal. And another really important ingredient is that individual or particles or units that compose the systems are generally orientable. They're rod-like, like a fish or a bird or a bacteria. It's a rod-like object. And so, like liquid crystals, they can exist in states with orientational order of various types. So I will be describing the system as sort of some kind of living liquid crystals, and we'll see what we can do with them.
Yeah, this may not be quite a fair question, but in the previous picture, do you have any idea, like, what is the motivating factor for why the birds are moving at all? Like, are they looking for food? Are they looking for partners? Are they looking for
It's not clear why. This has absolutely nothing to do with what I will talk about. However, it's not clear why they're moving. But the kind of thing that is really, so perhaps, they might be looking for food. I don't think they know why they're moving, okay? But the things that are really interesting, maybe somebody doesn't know, I'll let you say, but the thing that's really interesting is to see, for instance, if a predator, like a falcon comes by and tries to approach this bird, the response of this flock is really the response of a soft balloon, if you like, that is deformed by this. So that's why people tend to describe the collective behavior. Yes?
Yes, I can remember in this paper particularly they were looking at how birds with the flock, they reduce their energy expense with flying. And a lot of the modeling actually has some very basic ideas from there. And the pictures are from the model by the way, not the real one.
So let me give you show you two movies of the two kinds of systems that I will actually, try to model microscopically in the second two lectures. One is a suspension of bacteria, or E. coli to be precise, and the other one is a layer of vibrated granular rock. And the reason I'm showing these two movies is because what I want to stress is that you see some kind of sort of similar, if you like, collective motion, this kind of swirling type of motion, although very different scales. The bacteria are about 2 micron in size. These rods are almost 5 millimeter in size, so these things are occurring on very different scales. But this kind of vortex-type, turbulent almost behavior in systems, by the way, that have overdamped dynamics, and this is kind of contradictory to anybody who knows anything about fluid dynamics, to see turbulence in a system which is a low or zero Reynolds number, if you like. I'll tell you what the Reynolds number is. So it's kind of typical in this system. And these are actually the two kinds of systems I'll try to model in microscopically later on in the talk, in the lectures. Another system I would like to mention, which I will actually, we have actually developed a microscopic model and derivation of hydrodynamics for this more complex system, but I will actually not describe this in detail unless somebody wants to find out. I can tell them privately. Is the cell cytoskeletal. So here's a cartoon of a cell, and of course it's enclosed by a cell membrane. You see the nucleus, and then you see in red, blue, and green a variety of filaments or long polymers, actin in red, microtubules in blue, intermediate filaments in green, which are all rather stiff polymer, very long persistence length, and they form a network inside the cell. They're cross-linked by small proteins of various types. Here is an image of the actin cytoskeleton of the skin cell of some fish, I think it's a trout. And you see there is a rather intricate network, so there is sort of this gel-like, if you like, structure. And this is something that serves both, as you could say, as the skeleton and the muscle of the cell. In the sense that it controls the shape of the cell, it plays an important role in controlling the ability of the cell to move, and it controls a lot of the mechanical properties and the mechanical response of cells. Now, what is this made of? Why do I say that this has anything to do with my bacteria, if you like? So, if you actually look at what are the ingredients of this cytoskeleton, well, I kind of already said that there is long filamentary protein, like filamentary actin or microtubules, which have very long persistence length in vitro for actin of the order of tens of microns, and for microtubules actually of millimeters. And they're cross-linked by many, many proteins. So the filaments themselves have a couple of important characteristics. They're polar. They're what people refer to as a plus end with a minus end. They're not rods. They're arrows. They're the head and the tail. And they are generally polymerized. They're not in equilibrium. They're always polymerizing at one end and depolymerizing at the other end. And this phenomenon is called thread milling. And in that outcome of this thread milling, you could think of it as if the filament is being displaced in sort of like bacteria in suspension. In addition, they're cross-linked by many, many proteins, but among the cross-linking proteins are clusters of motor proteins. Most of you know what a motor protein is, but very simply, motor proteins are things like kinesin and myosin that are capable of transforming the chemical energy from the hydrolysis of ATP into mechanical work and literally walk along one of these filaments in a directed fashion, always towards either the plus or minus end, depending on the particular motor protein in question. And a small cluster of such motor proteins, as shown here, can cross-link to filaments, and by sort of walking, let's say one head on one filament, one foot we would say, on one filament and one foot on the other filament, they can exchange forces and torques among the filaments, therefore sort of continuously remodeling this network. And it is in this sense that this is an active network, which an energy input at the level of the individual filament, not unlike, if you like, from a large-scale point of view, the vibrated layer of granular rod, where the energy input is from the vibration, or the suspension of bacteria. So that's another system that falls into this general paradigm. And what these monofilament systems do, as I said, in vivo, they do lots of really important stuff. Among other things, they control the motility of cells. Cells crawl, move on substrate. Here's an example. This is actually the kind of skin cell from which the image of the cytoskeletal network was taken. See, it has this big flat area called the lamellipodium, and inside there is where this active active network sits, and it and drives, if you like, the motility of the cell. Cell moves with a variety of speeds. These are some of the fastest 15 micron per minute. These are, of course, are much slower. You can see from the duration of the movie. But the other really interesting thing is that it has been shown that if you just take a fragment of a lamellipodium, and actually you probably have to poke it in this case, it will move. So you don't need the nucleus to get this material, this active gel to move. It seems like motility, the ability to start moving, is actually a material property. So it might be interesting to see if we can describe the properties of this material that has the ability of going from a non-moving to a moving state as physicists using ideas of conduction physics. Now, in vitro, if you take out, you make a suspension of just, say, actin filaments with the corresponding motor, which is myosin, or microtubules, which are corresponding motor, which is kinesin. So you make a suspension of filaments and motor in a petri dish plus a solvent, and you watch at what happens as you increase the concentration of the motor proteins, which, remember, are capable of acting as active cross-linkers and move the filaments around, if you like. What you see is that what is imaged here are the filaments, although you can always see the concentration of the motors mostly it's the filaments that are imaged here. For low concentration of the filaments, you see sort of an isotropic state. The filaments, this is a quasi-2D system, the filaments are in the plane, they're sort of oriented in all direction, the first image. As you increase the concentration of the motor proteins, it appears that these motor proteins drive the formation of sort of interesting patterns, the spiral type patterns that look like vortices near the center, but then they splay out, and these aster type patterns. And with the different motor proteins, you still get patterns, but you don't get spirals, you only get asters. So somehow, the physical properties of the motor proteins are important in determining the type of patterns that is formed. And this is just a different type of filament, a different type of motors. And to a physicist, and we'll talk about this later, these patterns, remember these are 2D rods, but they're not rods, they are arrows, so they're like 2D spins, if you like. So to a physicist, these patterns are very much reminiscent of the topological defects of a vector field. And so we like to develop some theory of these driven filaments that has, where we are then capable of understanding this pattern in that way. And one more system I want to show you, which is now not a living system, but I thought this result would appear with this kind of. Another thing that one sees in this kind of system are usually unusual long-range correlations. This is a vibrator layer of granular rods that I was talking about before. And notice that I want to talk about only a 2D layer of rods, because one important ingredient in the system is that distinguishes them from others is that the system is maintained out of equilibrium by some energy that acts on each unit. Now, if you vibrate a 2D layer, then you have energy on each unit. But if you vibrate, as probably Steve will talk about, 3D granular system, then if you vibrate the bottom, clearly you're not vibrating each unit. So that's why I'm referring just to 2D layers of granular rod. So this is a layer, fairly dense layer of granular rod, and the inside of this picture here shows the mathematical parameter that tells you how much orientation, alignment of the rod there is in this system. And actually data for 3 different area fractions, and at the lowest, that is essentially no order, this is actually the highest one, and the 2 highest ones, there's quite a bit of nematic order. Now, if you actually measure density fluctuations in this system, to measure density fluctuations in any system, you expect that the variance of number of fluctuations will scale like the root of n, so that if you take the ratio of the square root of variance to the number of particles, that goes like 1 over root n and goes to 0 in the large system size. Well, in these systems, that doesn't happen, because this plot here is delta n divided by root n. There should be just a constant, and it is a low density when you have non-nematic order. But at high density, you see that this still increases almost linearly. So you have very large number of fluctuations, which in principle will not allow you to use the tools of some of the tools of equilibrium statistical mechanics. So that's another puzzling feature of this system. This has been seen only in this inanimate system. Nobody has actually done this kind of measurements in bacteria. As a theorist and as a physicist, I would say, I don't know why, but that's rather much harder to do. So what's the point here? Why should we be interested in this stuff? So we see that there are these quite different, seemingly quite different systems. And people have been studying them for some time, and it's becoming apparent that some of the features that these systems exhibit can actually be described by sort of the same continuum theory, the kind of hydrodynamic theory I'll be talking about. Now, the hydrodynamic theory won't be able to describe everything, but captures quite a bit of their behavior, doing the kind of things physicists do like to do, which is sort of provide a unified description of many different phenomena. And so that's kind of what I want to tell you about here. So the kind of relative behavior that I'm talking about include things like the onset of directed large-scale motion. The system, even the bacteria or the birds, if you like, may go from being at rest to start moving. That's a kind of, can we understand that as a kind of phase transition? Can we understand cell motility, if you like, as a kind of phase transition? There are certainly a lot of order-disorder transitions, transitions from states that are orientationally disordered to states that have some orientational order, or some, generally not long-range orientational order, but some large-scale orientational order, including the possibility of quasi-long-range orientational order in 2 dimensions, pattern formation on various scales, new correlation, like the giant number fluctuations, and so on. And then we won't have time to go through these in these weeks, but the system exhibits very unusual mechanical and rheological properties, which won't be like you to understand. It cell stiffens when you stress it, and tends to adapt its mechanical properties to the environment. So we're going to be trying to do the theory of these living liquid crystals. And the theoretical work that people have done in this field, the main goal, as I already said, has been to use the tools and ideas of soft-on metaphysics, mainly hydrodynamics and the notion of broken symmetry, to develop this sort of effective field theory. And do things such as the things we know how to do, characterizing phases and order structure, understand the role of noise, understand the rheological and mechanical properties of the system. But in particular, what I think is important to try to do is to really use all of this to try to understand how far can physics go in understanding its behavior, meaning what behavior can you explain by putting in just physical interactions, such as to the volume or hydrodynamic interactions with the fluid, and what kind of behavior cannot be explained by that, but actually needs to, you have to put in things like some biochemical interactions or chemotactic interactions, which are in some sense beyond the scope of what I will be talking about today. And can we think of this unsettled motion as sort of a material property, as sort of some type of non-equilibrium phase transition? And the second thing, so the first thing is develop this sort of coarse-grained theory and use it to try to understand this. But of course, we also would like to understand the microscopic mechanisms that are responsible for the large-scale behavior. And that's where it would be important to try to derive the microscopic theory from specific microscopic model and try to bridge the gap between these two. So, the theoretical work that has been done in this field, it can sort of be grouped into 3 classes. There have been a lot of numerical simulation and study what I will call rule-based model. Rule-based model, first one was introduced by Mastichek back in 1995. He sort of the person who started this field. And the model introduced to describe this kind of collective dynamics, collective motion. If you like, is a very simple one. He said, well, let's assume we have point particles in the plane which are moving with a fixed velocity v naught at all time, and at every time step they look at their neighbors and within some radius, and they change their angle, the direction in which they are moving, to adjust it to that of their neighbor. So they align with their neighbor locally, and then you go on, and clearly this model, and there is noise, they do this in the presence of noise. This model, it's not very difficult to show that we exhibit sort of a transition as a function, if you like, of the strength of the noise from a disordered state where all the guys are going in all different directions to an ordered state where everybody is moving on average in the same direction. But it's not a very satisfactory model in the sense that you're putting in the alignment by hand. You're saying, okay, I look at my neighbors, I align with them, and then I move on. And of course, you get the transition to an aligned state. What we would like to understand is whether this kind of transition from a non-moving to a collectively moving state can occur as a result of physical interactions, which are not looking at my neighbors, but maybe colliding with my neighbors or interacting with my neighbors through the fluid, if I'm bacterium sitting in the fluid, or something like that. So that's the kind of questions we want to ask, and that's why I want to go beyond this kind of models, which actually, however, are very rich and they're very interesting also to study. The other two types of work, there are two classes of work that have been done in this field, are sort of looking at the large-scale behavior, but sort of writing down phenomenological hydrodynamic equations for this system. This has been done by many authors, some working in the context of flocking of birds, some working in the context of maybe bacterial suspension, some working on models of the cytoskeleton. And I will tell you a little bit, mostly next time, a little bit today also, how we do this, how one writes down this phenomenological hydrodynamic equation. And it's a very powerful theory because it's generic, only depends on the symmetries of the system, and you can go very far with it. But when you use this approach out of equilibrium, you have no idea what the parameters you put in the equation are, you cannot estimate them. And so it has some drawbacks. But that's what we will be working with in the first two lectures. And then, as I said before, the second two lectures I actually will show you how this hydrodynamic equation can actually be derived for specific model systems. And then in particular, and that's mostly work done by us, I will mostly show you the two model systems, which are the vibrated rod and this very simple model for bacteria in suspension. Now, this was a sort of a very generic introduction, but I thought I wanted to do this because I thought that there are people here from very different backgrounds, and I wanted to try to give you some feeling of the kind of systems I have in mind. If there are any questions about anything I said, I was very descriptive, so it would be a good time to ask.
Can you elaborate why you're not talking about the rule-based models? Because it seems like
because
really
I only have 4 hours and not 6. No, I don't talk about the rule-based model. It's just a choice. I mean, I just chose not to do that. I'd be happy to talk to you about it, but rule-based models are very nice. Most of the time what you can do with them is either mean-field theory or numerical work. And I was more interested in describing some sort of analytical tools. So it's simply a choice. I don't mean to say they're not interesting, not at all. There is actually very interesting, still somewhat open question about the Bichet model of multiplications, which has to do with the order of the transition. Whether the transition from this disordered non-moving state to this moving state is actually continuous or first order, which originally thought it was continuous, but is now quite a bit of work saying it's most likely to be first order. So there are lots of very interesting questions there. I don't mean to say there are. Okay, anything else? Okay, so what I'd like to do now is kind of remind you a little bit about some things that probably you learned in some statistical mechanics classes. I'm using the word hydrodynamic here in a rather general sense. As I said, it's sort of an effective field theory that used to describe the behavior of a system composed of many interacting degrees of freedom, 10 to the 23, and you do some type of coarse graining, and you go from the many interacting degree of freedom to a description in terms of a few fields of variables, maybe 5, maybe 10, certainly far fewer than 10 to the 23. And that's very much what people do also in high condensed matter physics, cosmology, and particle theory, and that's what we do in soft condensed matter physics. And there are sort of two ways of doing this. One is phenomenological. You just write down the equations of symmetries, and as I said, it's a very powerful way to proceed. It yields you a generic theory that applies to everything. But there are no, if you're out of equilibrium, if you're in equilibrium, there are many constraints imposed by the fluctuation dissipation theorem that allow you to determine the parameters in the equation. If you're out of equilibrium, fluctuation dissipation theorem no longer applies, and the parameters in the equations are simply undetermined, often even inside. And so it's not as powerful as it is near equilibrium. Another alternative you have is to start on some microscopic model and use statistical physics to actually do the coarse graining and derive the equations. But of course, this has some other problems, which is that you have to make some approximations, usually low density, for instance, and you will derive equations, that, if everything is working out well, have the same structure, all the same terms, as the equations that were written down phenomenologically. And you will have explicit values for the parameters in the equations, although, of course, the specific values are model dependent and approximation dependent. And it's really important to sort of do both, as a matter of fact, to get a complete description of the system. So I want to kind of tell you a little bit about how one does this today, about the phenomenological approach. Now, clearly the first step is to choose this macroscopic or hydrodynamic field. When you disturb the system from equilibrium and then you watch it relax, how it relaxes the equilibrium, of course, is determined by the macroscopic interactions among the many, many interactive fields of freedom. But there are a few collective excitations, like the phonons in a solid, that relax more slowly, so they sort of stand out, and they form a set of what we call slow variables that are going to be the one we will choose for this macroscopic description of the system. And there are two classes of such slow or hydrodynamic variables. The densities of conserved variables, such as particles, momentum, and energy in the fluid. And if you are in a system that can exhibit spatial order, that can exist in an ordered state, like a magnet or a ferromagnet, that can order, there are also broken symmetry fields that also are hydrodynamic fields. What do I mean here by the general property of these low variables is that the relaxation to equilibrium of a fluctuation, of a large scale fluctuation in one of these low variables, we relax at a rate, omega, that goes to zero when the wave number goes to zero or the wave length goes to infinity. So they are infinitely long-lived in the limit of long wavelength. So the first thing we need to do is when we start with the system, we need to identify these two classes of variables. Let me give you an example. The first one, conserved field, is familiar, but let's just go through this. So suppose we consider a colloidal fluid, large colloids, micrometer-sized colloids in a solvent. And clearly, in this system, there is only one conserved variable, which is the number of colloidal particles, the density. If I think of the solvent as just a momentum sink, it just provides the damping, the momentum is not conserved. So I only have one conserved field, the density. Now, if I consider a fluctuation in the density of colloidal particles away from its equilibrium value, such fluctuations generally will occur in a thermal system with probability, which is just thermal, into the minus free energy divided by kVt, and they relax back to equilibrium in a way that is controlled by a conservation law, that is the rate of change of the density fluctuation is the gradient of a current, and the current itself is controlled by gradients of density, the A constant, which is a diffusion constant. If you combine these two, you get the sort of the simplest of hydrodynamic laws, which is a diffusion equation for this density fluctuation. I have considered small fluctuations, so this is a linear equation, so I can immediately go to Fourier space and solve for the time decay of fluctuations of a given wave vector. And the decay rate clearly is just decay squared. So this is an example of a hydrodynamic mode. A long wavelength, k equals 0 fluctuations of density, becomes infinitely long-lived. And this effect is actually deeply connected to the translation of symmetry of the system, essentially. So the infinite fluctuation of density, it's related to the translation of symmetry of the system. So a real fluid, rather than a fluid of colloidal particles, will also have momentum and energy density as conserved variables, but they all behave in similar ways, and their decay is characterized by this kind of hydrodynamic mode. Defined this way. Yes?
Excuse me, what is conserved here? Is it
the number of colloidal particles is conserved, right?
And why do you call it a driven system?
No, this is not a driven system. So what I'm trying to do now is I'm stepping back a minute. I gave you sort of an overview of the kind of system I would like ultimately to describe. Now I'm stepping back a minute, and I want to kind of remind you about tools we have available to describe this kind of systems, to develop a large-scale description of the systems. And for a minute, I'll be talking about equilibrium systems now. So the first thing I said is that I want to develop this hydrodynamic theory. That is, I want to write continuum equations for the slow field, The slow fields are conserved variables and broken symmetry variables. This is an example of a conserved variable in the simplest system I can think of. Now, the system I'm interested in are made of these rod-like objects, so they can also order the states with orientational order. So they are systems that will exhibit broken symmetries. So now I want to give you an example of a broken symmetry field. And again, this is an example from equilibrium, and the simplest example I can think of is the orientational order in a nematic liquid crystal. And actually, since I'll be describing what I've been calling living liquid crystal, the nematic liquid crystal example will be very relevant to what I will be talking about. But so far, this is just equilibrium. So what's a nematic liquid crystal? It's a liquid of rod-like molecules. In fact, even just hard rods can undergo a phase transition as a function of density from an isotropic state, which is a liquid and exhibits no orientational order, the rods are on average responding in no direction, to a liquid state that has already, however, broken orientational symmetry. That is, the rods are on average aligned with a fixed direction in space. And this symmetry, the orientational symmetry in this transition, which was studied very long time ago by Gonzaga, is spontaneously broken. And it occurs because actually a competition between translational and rotational entropy. If you put enough sticks on a plane, they can actually gain translational entropy by aligning, although they lose orientational entropy. And that's why they prefer to order, if there are enough of them, they prefer to order into a state which is called a nematic state. So what is the broken symmetry field? Yes?
And the fact that it's slow dynamics, is that not
it's not slow dynamics here. I'm going to tell you next. So the question is, why am I saying that there is a slow field associated with this? Okay? That's what I want to tell you next. Oh, that's just that's why the transition occurs. This is actually a photograph taken by Arshad Kudroli of Clark University, and this shows you why you get a nematic if you put enough rod-like objects on a plane. And it's entropy. Okay, but why should there be a slow field associated with such a transition? So let's now think about the order state, this nematic state where the rods are on average aligned in one direction. One important point about the nematic liquid crystal is that it is a aligned state of rods. Rods are heterosymmetric, so the order state, the direction of order will be characterized by some unit vector n, but the order state has to be symmetric in changing n into minus n, because there is no difference between these left. The two directions are the same. So suppose I want to describe order in this system. Well, each rod, the orientation of each rod could be characterized by the angle it forms into fixed direction in space. I can construct some mean measure of their direction. I could calculate the mean cosine of the angle, but since the rod has no head and tail and the state has to be symmetric in changing n into minus n, clearly that would be zero on average. So the quantity that will be non-zero is actually a tensor, which is called the alignment tensor in liquid crystal. That's the order parameter for the liquid crystal order. If you like, it's proportional to the square, is the mean of the square of the cosine rather than the mean of the cosine. And this quantity will be non-zero in the order state and zero in the disorder state. For the simplest of liquid crystal, which is a crystal of rod like this one, at the macroscopic level, there is only one preferred direction, denoted by this unit vector, which is called the director. And so the alignment tensor can be written in terms of a magnitude, and it's a symmetric traceless tensor, so in terms of the component of this unit vector. Now, the magnitude of the order parameter field is actually the order parameter. This S is zero in the order state and zero in the disorder state and non-zero in the order state. The director is what I call the broken symmetry field, and this is the slow variable that I'm interested in. Why is this the slow variable? Well, let's think of the order state. Everybody's on average aligned in one direction. Clearly, the energy of the system cannot depend on the direction. If I do a uniform rotation of the system, the energy doesn't change. Now let's think about what it means to do a local fluctuation of the director at some wavelength lambda, some wave vector k. That's not a uniform rotation, it's just a local rotation. But clearly, that fluctuation must cost no energy in the limit where the wave vector goes to zero or the wavelength goes to infinity, because in that limit, it's a uniform rotation. So this is a variable that has the property that fluctuations cost no energy when k goes to zero. That is, they must decay in slow modes, modes that go to zero when k goes to zero. These are hydrodynamic variables. More properly, they're called Goldstone modes or Goldstone fields, but they are the broken symmetry fields are hydrodynamic fields, just like the constant densities. And I went to this because I wanted to stress there's a lot of confusion even in the literature sometimes, that the hydrodynamic variable is not the order parameter itself, but just the broken symmetry field, the director. Of course, the energy of the ground state does depend on the value of S, which is actually the order parameter. Like in a magnet, the energy of the order state will depend on the magnitude of the polarization, of the magnetization. It doesn't depend on the direction of the magnetization. Okay? So that's the kind of things you need to think about if you want to construct a hydrodynamic theory phenomenologically. The first question you want to ask yourself is,
Excuse me, can you repeat what is S?
What I said?
No, can you repeat what is S? So
S is the so this is a tensor that you construct. Is a symmetric. If you are in 3 dimensions, I'm in 3 dimensions. Here is a symmetric traceless tensor. Right? Now I calculate this average. Now at the macroscopic level, I can write it for this system of rod, which is uniaxial, right? The only spatial direction is n. I can write it this way. S, if you like, is, I call it the magnitude of the tensor. I mean, it is a little bit, let's use in quotation, but S is the magnitude of the order parameter. S is the quantity that tells you if you are in the disorder state or in the order state. S equals 0 is the disorder state. On average, there is no control direction. S finite is the order state. Of course, S can still range from, say, 0 to 1, meaning S equal 1 will be more order than S equal 1S. It's just like the magnitude of the magnetization in an Heisenberg ferromagnet, if you like. N is a unit vector which tells you the direction of the broken signal, which is fixed spontaneously by the system. So the energy cannot depend on that. And so N is a hydrodynamic variable because infinite wavelength fluctuations in N must cost no energy. It's a massless mode as opposed to a massive mode. Okay? So if you're interested in describing systems which have some kind of order, you have to worry about identifying this kind of variables as well. Yes?
anyway, so the hydrodynamic variable doesn't respect the symmetry of n plus and n minus?
Well, I picked a particular system. I picked a nematic. I have to worry about symmetries of the system, and I have to worry about conservation laws, and I have to worry about broken symmetries. Okay? I have picked a particular symmetry. I have a particular system here to use for my example. I picked a nematic liquid crystal. The nematic liquid crystal happens to be, and I picked the simplest of nematic liquid crystal, a collection of rods, hard rods, can order into this nematic liquid crystal state. The rod itself is entel-symmetric. The macroscopic order state is also entel-symmetric. Once the system orders, say all the rods are aligned in this direction, clearly this direction is different from the other direction. But the system is symmetric in changing the direction. So the orientation is the same, but the is symmetric in the direction.
Yeah.
So if I were to write the energy of this system, it has to be even in n, because n and minus n are the same thing.
Yeah.
Okay? So for this particular system that has this symmetry, I'll have this particular broken symmetry variable, which is not really a unit vector, if you like. It's a unit vector living on a sphere. It's a double-headed unit vector.
Okay.
Okay, I'm not sure. Maybe I don't understand your question.
You're concerned that you're using a vector to describe a double-headed vector. Well,
okay. So yeah, if that's your concern, yes. If I actually, when I go and do a theory of this system, I better keep in mind that this is not a vector. It's a unit vector living on is point on the surface of a sphere, or is a double-headed unit vector, and I have to be careful with that. Absolutely.
It's a little bit. I don't know if this helps. It's a little bit like gauge theory, where you reduce the variable redundant. So anytime n goes to -n, you have to remember that that's the case. So, but equation of motion will be even in n.
Now, let me just say one thing. Now, the vast majority of pneumatic liquid crystals in equilibrium are of this size. But pneumatic liquid crystal, by definition, is of this size, has this symmetry, n going to -n. The systems I'm interested in describing, actually, just think of these moving bacteria. They can actually order both in states that have pneumatic symmetry. Of course, the guys are going one way, alpha going the other. But in states also that have polar symmetry, sort of just like a magnet now, where now my unit vector is a real unit vector, and the system does not have this symmetry we're talking about here. Okay, so I'll let me conclude that. There was another question.
Well, yeah, without putting in like the dynamics of the interaction, how do you know that the delta n sub k is decay exponentially?
So that's the whole point of this. But near equilibrium, you can show that this is the case, and that's all I'm talking about here. But that's the whole point of this sort of phenomenological way of writing, or generic. People call it generic. I mean, because people don't like the word phenomenology. And it's true. This is actually very generic, very general. Of writing down hydrodynamics. You base it entirely on symmetry, conservation laws, and so on. And the equations you write are supposed to be independent of microscopic details. It's like constructing the theory of phase transitions. It's supposed to be independent of microscopic details, so they don't depend on. Now, here, a small fluctuation will sort of always decay exponentially as soon as you know that the equations that describe its decay are first order in time. And the fact that the relaxation rate is equal to 0 is just simply a statement that it's a massless mode because the energy doesn't depend on the direction for uniform rotation. Yes?
Is this in any way related to BGK models?
Sorry?
Is this related in any way to BGK models?
BGK models. Bone growth. Yvonne, you really mean that?
No, I forget the whole thing. I only know BGK.
Well, I mean, these kinetic models, do you really mean that? I mean, because I know what these are, but I'm just surprised anybody else would. But you really mean these kinetic models that you write down?
No, it's very approximated relation time. So you have only one instead of an exact solution.
Yeah, so it is what I'm talking about. Well, no, it's not. Those are very specific kinetic models you make for, say, model the Boltzmann equation or things like that. This is truly general. This is fun. It's just linear. It's right. Just linearized hydrodynamics. I mean, you have a relaxational dynamics. The equations are first order in time. Differential equation of first order in time. You linearize about equilibrium. The decay is going to be exponential. That's really all there is. Okay. So maybe let me try to be even a little bit even more specific and simpler. And let's just actually do this specifically for a simple fluid. Suppose I want to write down, I want to construct an Navier-Stokes equation, okay? And I don't know anything about it. How do I do this? All I know is that I'm dealing with a simple isotropic fluid, and I need to, first step, I said, is identify the hydrodynamic variable. And in a simple isotropic fluid, I don't expect to have any broken symmetries. I'm not interested in this thing with no ordering, and it's not becoming a crystal, it's not doing anything. So there are no broken symmetry fields, there are only conserved densities. And the other important assumption is that I want to construct a set of hydrodynamic equations that, by assumption, will only contain these variables, these hydrodynamic variables, and their gradients. They have to be closed equations in these variables. So how do I do this? Well, I first identify the symmetries of the system, identify conservation laws, and then I'll show you. And then I have to close the conservation law relate conserved variable to a flux. I have to close the conservation law by figuring out how the flux is written in terms of the hydrodynamic variables. And since I'm only interested in large-scale physics, I will always only keep giving terms in gradients of the hydrodynamic fields. So for a simple fluid, The conserved densities are just density and momentum and energy density, but I'm assuming, let's just consider isothermal processes. I'm even simpler. I'm not going to look at variations of density, so I'm only looking at of energy, I'm only looking at density and momentum. What are the symmetries of a simple fluid? Well, of course, rotational invariance, space and time translational invariance, and an important one, Galilean invariance. The equation must look the same in frames that are moving with respect to each other with a constant velocity. So what are the conservation laws? The conservation laws are just relate the rate, so these are the two hydrodynamic fields, density and momentum, that also define the flow velocity here, which commonly transact in the system. Conservation law relate the rate of change of the field to write them as gradients of some fluxes. The flux, the density flux is just the momentum itself, and the momentum flux determines the rate of change of the momentum density. These are exact. You can actually derive these exactly from Hamiltonian dynamics for the system, and you get exact expressions, if you like, at the microscopic level for these fluxes, but that doesn't help you because you don't know what they are. In fact, the crucial thing is to figure out how to write expression for the fluxes in terms of the hydrodynamic field, the density and the momentum density. Well, for the density equation, it's easy because the density flux is itself a hydrodynamic field. So actually, this is the exact conservation law, which is already closed, and you have to do nothing there. But what you have to do is to figure out how to write the momentum flux as a function of density, momentum, energy density, and gradients of these various fields. And close the equation, so simply without making any statement about the microscopic behavior of the system. One way to do this, again, Fermier equilibrium, is to assume sort of local thermodynamics and calculate something called the rate of entropy production. So again, it's a simple fluid. And I am being a little bit sloppy here. You can find more precise formulations in many places, but the free energy essentially there'll be some kinetic energy density and some density that depends only on the density field. That's really the only variable in the problem. But I'm not going to specify the form of this quantity. I can calculate the rate of change in time, which I call the entropy flux. And I will do that by taking time derivatives in here, and then inserting, using the conservation law, and using the local thermodynamics, assuming the second law of thermodynamics essentially, I can actually rewrite the rate of entropy production in terms of, as the product, if you like, as the sum of a bunch of terms, where each term is the product of a flux times a driving force that can drive the system out of equilibrium. And the driving forces in a simple fluid are gradients of, let's call it chemical potential, but for the simple fluid I'm interested in, you could just say gradients of density, because I'm assuming energy doesn't really change, so gradients of density and velocity gradients. These are the driving forces. There is a driving force associated with each hydrodynamic field and the corresponding flux. And I can actually derive this, and if you look at the notes, the reading I have suggested, you can find a way, it shows you how to derive this, actually fairly simple. You can derive this expression for the rate of energy production. So the important thing is that for every hydrodynamic field, there is a corresponding flux and a corresponding driving force that can drive the system out of equilibrium. And the rate of entropy production is essentially the sum of terms which are products of the flux times the corresponding force. Now, if you're dealing with a reversible process, so that's now displacing the system from equilibrium in some way. If you're dealing with a reversible process, this rate of entropy production has to be zero. So this whole big integral has to be zero, and has to remain zero. Each term has also to be zero independently, because you can imagine displacing the system from equilibrium by either changing the density or inducing velocity gradient, and you can do this independently. So if the process is reversible, the only way this can remain zero is if these terms are independently zero. And this gives you expressions for what are called the reversible part of the fluxes. It tells you that the reversible part of the momentum flux is just the density times the flow velocity, and that the reversible part of the momentum flux is sort of the momentum transported by convective processes, and in this case, the pressure. Right? That's what the term is. Now, if you're dealing with an irreversible process, then R has to be positive, and that tells you that there has to be an additional contribution to these fluxes, which is called the dissipative part. And that part has to have a particular sign, and there has to be certain property under time reversal to ensure that it describes dissipation. And for a simple fluid, it can only depend on velocity gradients, and it's a second order tensor. In an isotropic system, the most general way you can write it is this, and you write interval two parameters, which are the shear and bulk viscosity of the fluid. So what I'm trying to tell you here is that you can do all these constructions just based on symmetry property, time reversal property of the system and conservation law, and identify exactly the so-called reversible part of the fluxes, and write down phenomenologically, in terms of using the symmetry property, the most general form for the dissipative part of the fluxes. You substitute this into the conservation laws, and you get the hydrodynamic equations. Conservation law for the density is unchanged, and the law of conservation for the momentum becomes the Navier-Stokes equation, which I'm sure is familiar to many of you. It contains this convective derivative, contains gradient from pressure, and it contains viscous dissipation. Notice, for instance, that it does not contain, it contains the term V dot grad V, but it does not contain a term like divergence of V times V. Now, why not? They're both at the same, these are equations for a vector field. I'm just writing down things on the basis of symmetry. I could either write down for this term and this term, but this term is not there. Why not? Because it violates, actually, one of the symmetries of the system. And you can actually show it does. Anybody have a guess for which one? Galilean, that's right. This is not Galilean. This is Galilean environment. This is not. Okay? And that's why in this construct, this term doesn't come out when you don't the solution. It doesn't contain terms of the order of, like eta prime, Laplacian, fourth order derivative of V, not because this is not allowed, but because I'm doing a theory of lowest order in the gradients. I'm keeping the lowest order terms in the gradients. In principle, you could have this term, and you'll be going on beyond the limit I'm considering here. So these equations can actually be written down just on the basis of symmetries and conservation laws. And they, as we know, they provide a very powerful description of the behavior of fluids. And so what I would like to do in the next lectures is show you how we do this now for a system which is out of equilibrium, systems like the suspension of bacteria or the cytoskeletal filament and motor protein system. Now, in the context of active systems, I just like to say one more thing. There are actually two approximations that will be often relevant and that I will be using. The first one is that often I will assume that the fluids I'm interested in are incompressible, that is, the density is constant. If the density is constant, the first equation simply becomes the statement that the divergence of V has to be zero. So that's the incompressible limit that I will often be using, and you don't have the first equation at all. The second approximation is that we are often interested in what's called a low Reynolds number. And I'd like to conclude today by, and what that means essentially is that, and I'll tell you more precisely, is that so you can rewrite this equation as the entire right-hand side of the equation is essentially the gradient of the stress tensor. These are sort of inertia. This equation is sort of like MA equal F. Is the field theory version of MA equal to F. So this is MA, this is the inertial part, and this is the force on the fluid element. The low Reynolds number limit is the limit in which inertia is negligible, and for the Navier-Stokes equation is simply written as the statement that the net force on the fluid element is zero. And that limit is relevant in the following situation. Let's imagine we have a body of size L, fluid, say, flowing, fluid of some density rho and viscosity eta, flowing past this body, and we write down a Navier-Stokes equation for describing this flow. Now, on the basis of just dimensional estimates, you can see that the viscous force is of order viscosity, velocity, divided by the square of a length. And the acceleration inertial forces are of size density times the square of the velocity divided by a length. If you take the ratio of these two numbers, the ratio of inertial forces to viscous forces, that defines the number which is used all the time in fluid physics called the Reynolds number, which is V times rho L divided by eta. And the Reynolds number, if the Reynolds number is very small, viscosity, viscous forces are small. If the Reynolds number is very small, you are in the regime where inertial effects are essentially negligible. And essentially, you can really describe the flow by setting this left-hand side of the equation to 0 and just looking sort of over that limit, just looking at the flow in the limit in which this gradient of the stress tends to be equal to 0. The opposite limit, where the Reynolds number is very large, inertial forces are large compared to viscous forces, is the opposite limit is the limit for which, for instance, you get turbulent flow in fluids. You can get turbulence behavior and so on. Now, in the kind of systems I've been interested in, such as the bacteria, the numbers that are relevant here are the size of the object, which is microns, even longer if you're worried about cytoskeletal filaments. Kind of velocities we're talking about are at most 10 microns per second, usually actually less. And so if you put in some numbers, and these things say you're swimming in water, if you put in some numbers, you will calculate a Reynolds number to be of the order of 10 to the minus 4, 10 to the minus 5. That is a very small Reynolds number. We are well justified being in this regime of Stokes flow, where the dynamics is over them. These things don't move to burst of acceleration. They just move to the fluid very slowly. There is no inertial response in the system. Yes, by the way, I want you to keep in mind that the movies I showed you the behavior which people have called bacterial turbulence. So this is kind of very interesting behavior we want to try to describe. We are in what in fluids people consider the non-turbulent regime, or as non-turbulent as it can get, and yet we are going to get all this kind of turbulent behavior. That's only one of the things we try to understand. By the way, there's a beautiful old article by Cosell in the American Journal of Physics called Life at a Low Reynolds number that I highly recommend as reading. So, I just want to conclude for today. I kind of give you a little bit of a tour about the kind of systems I'm interested in, and I try to give you a little bit of a tutorial on how one constructs hydrodynamics theory at this phenomenological level. And next time we'll do this construction phenomenologically for active systems, and we'll actually also use the hydrodynamic equations to describe some of the behavior of the system. So I think I will stop there for today.
Questions, please.
I have a question about the little plug-in with the Ransdorfer theory. So I'm very ignorant about the whole thing. I'm just curious, first of all, where does the width of the rods, does it play any role in the Ransdorfer theory?
The width of what?
The width of the rods. Like you said that you have, it seemed like you just have sticks that has no width to it.
The Ransdorfer theory. I thought you were talking about the...
Ransdorfer theory.
No, okay. Well, the estimate, I gave some estimate, but that would be for very long intervals. The aspect ratio, I think, plays a role in determining the order of the transition. This transition, the non-trivial pneumatic transition, in 3 dimensions for the first order. But there are still arguments about this, but I think it can show that if the rods are too short, it can actually become continuous. It also becomes continuous in 2 dimensions. All of these, of course, in theory.
But this this is like a well-established result, you're saying it's not so well-established?
No, this is also well established.
Within an quantitative theory, that ratio, there's some critical value ratio, but otherwise you don't get pneumatic fit. Not at all. Not at all.
Yeah, that's true also. Yeah.
Non-Zygote states, you also get continuous transition over the ratio versus
No, I couldn't hear what you said. On Zygote theory in 3 dimensions.
Okay, well, okay, yeah. Well,
I think the ratio is length over width should be larger than 4.
Can I ask a second
Sure,
question about
go ahead.
So, again, being completely ignorant about this, I'm just curious, if I had a finite lattice system that I could then put in some number of sticks, and as a function of the number of sticks, just enumerating all the possible geometrical states, can I understand, is there some interesting transition phenomena as I increase the number of sticks, like the entropy, suddenly changes as I increase the number of sticks?
I think that, if these are hard sticks, entropy is all there is.
Right, no, but I'm saying that if you just, if I was just doing an enumeration study, like I have, say, a 4x4 box and I have sticks at length 3 and I stick them in there. And
I would imagine, I don't know if somebody has done this, maybe Theo does, I don't know, but I would imagine that yes, you would see precisely, you would see that. If you could do this, that eventually it becomes favorable for the system, for the state, precisely because of counting return.
You can't do it on a lattice, right?
Yeah, sorry, it could not be done on the lattice. Because it's really a competition between the entropy of translation and the entropy of rotation. So yes, it cannot be done on a lattice. It would have to be done in So probably, I suspect people have not done this. Because it seems like it would be complicated.
Well, Flory did it on a lattice in the sense that he looked at long rods that were made up of sort of short segments that were on a lattice, right, and got the I-to-N transition that way.
Further questions? Yeah, please.
When you were talking about the low Reynolds number, you neglect the inertia term. You don't have to worry about the order of magnitude of the pressure term.
The pressure I will keep. I have to keep the pressure. So,
you can check for your systems that that's the same order of magnitude.
For equilibrium systems it is. Yes, but in general the pressure is one of the, it's part of the force, if you like. So the rotary force. It turns out if you are actually dealing also with incompressible liquid, then you can actually do the pressure too, but that's another story.
Okay. Further questions? We have 5 minutes. Want to go? Okay. If not, then we continue tomorrow, and we come back again here after the break at 4:15.